Hello friends, welcome back. In previous video we have seen the valence bond representation of tetrahedral and square planar complexes. Now here in this video we have to study the valence bond representation of trigonal bipyramidal complexes and the octahedral complexes. So let's start with the first one, that is the trigonal bipyramidal complexes. So we are having the third, that is the trigonal bipyramidal complexes. Now these trigonal bipyramidal complexes, they are formed by the dsp3 or sp3d hybridization of the metal atom or the ion, in which the atomic orbital uses the dz square atomic orbital. So here we can say that these are formed by the 1d, 1s and the 3p atomic orbitals. So the first example is the FeCO5, that is the iron pentacarbonyl. It is a neutral complex. The electronic configuration of the Fe, which is having the atomic number 26, is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Or we may write it is having the argon core, that means atomic number 18, remaining is the 4s2, 3d6. So we are having the 2 electrons in the 4s and the 6 electrons in the 3d. Now here this Fe is having the no charge because it is a neutral complex. So let's put the electrons in the box diagram. So we are having the Fe in the ground state. We are having the atomic orbital. The first one is the 3d atomic orbital, then 4s atomic orbital, then 4p atomic orbital. So we are having the first electron, the second electron, third electron, fourth electron, fifth electron. Then the next one will be paired, that is the sixth electron will be paired. Further in the 4s, the first electron and the second electron. Now as it is showing the dsp3 type of hybridization, that means one of the d atomic orbital and the 2 electrons from the 4s, they should be shifted to the adjacent position, right? So this Fe, that is the central metal atom, it undergo excited state configuration. So Fe with the excited state electronic configuration, in which we are having again the 3d atomic orbital, then the 4s atomic orbital and the 4p atomic orbital. Now here just the 3 electrons, that is 1 from the 3d and the 2 from the 4s, they are shifted in the adjacent 3d, in which the remaining 3 they becomes the paired. This is called as the excited state electronic configurations. Like this, the first electron shifted in the adjacent, then the next electron from the 4s will be paired up in the 3d, and the second electron from the 4s paired up in with the second electron. So we are having the first electron, second electron, third electron, fourth electron, right? They are the unpaired electron. Then the fourth electron, it is as it is. Then this is the electron from the 4s. This is again the electron from the 4s, and this one the electron is from the 3d. So by using this, we may say that the 1s, 1p and a 3p atomic orbital, they are vacant, which suggests the dsp3 type of hybridization. So the complex, that is the FeCO5, in which again we are having the 3d atomic orbital, 4s atomic orbital and the 4p atomic orbital, right? Again we are having the electrons from the metal, that is the first electron, second electron, third electron and the fourth electron. Then fifth will be paired, sixth will be paired, seventh paired and the eighth pair. Whereas the remaining, the first pair of electron, second pair of electron, third, fourth and the fifth, these are the 5 pair of electrons which are given by the ligands, and the ligand is the carbonyl ligand, or we may say that these are the electrons from the 5 carbonyls or the 5 ligands. Further we can say that as all the electrons are paired, it is a dimagnetic in nature, then the observed and the magnetic moments of the complex is 0. Why? Because the number of unpaired electrons are 0. Then the central metal atom Fe undergoes dsp3 type of hybridization, which suggests the trigonal bipyramidal geometry. So the trigonal bipyramidal geometry is like this for the FeCO5, in a trigonal fashion, we are having the 3 carbonyls, then the out of the 2, 1 carbonyl is above and the below, second carbonyl is below, which is called as the trigonal bipyramidal geometry. Then the second example is the CuCl5 3- ion. Let's see the electronic configuration for the copper, which is having the atomic number 29, is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. Or the electronic configuration is the argon core, that means atomic number 18, remaining is 4s1, 3d10. Here the oxidation state of the copper is +2. So the electronic configuration for the Cu2+, that means atomic number is 27. That means we have to remove the 2 electron. 1 electron is removed from the 4s and the second electron will be removed from the 3d. So it is 1s2, 2s2, 2p6, 3s2, 3p6, then 4s0, 3d9. Or it is having the argon core remaining as 4s0, 3d9. So let's put these 9 electrons in the box diagram. So we are having the Cu2+ in the ground state, for which we are having the 3d atomic orbital, then 4s atomic orbital, then 5p atomic orbital. 4p atomic orbital, 3d, 4s and 4p. So we have to put the 9 electron in the 3d atomic orbital. So this is the first one, second one, third one, fourth one and the fifth one. They are the unpaired. Then the 6th one will be paired, 7th will be paired, 8th will be paired and the 9th will be paired. So these are the 9 electrons in the 3d atomic orbital. Whereas the 4s and the 4p, they are vacant. Now here we are having either the dsp3 type of hybridization or sp3d type of hybridization. Now here the dsp3 type of hybridization is not possible because we can't shift this last electron to make this 3d atomic orbital vacant. So instead of this inner 3d orbital, we have to use the outer 3d orbital. So the Cu2+ in the excited state, we are having the 3d atomic orbital, then the 4s atomic orbital, 4p atomic orbital, and the last one is the 4d atomic orbital, in which we have to shift the electron, or we have to use the 4d atomic orbital for the sp3d hybridization. So we are having the first electron, second electron, third electron, fourth electron, fifth electron, then the 6th, 7th, 8th and the 9th. So these are the 9 electron and the 3d, whereas this is forming the 4sp3d type of hybridization. This is called as the sp3d type of hybridization, in which we have to fill the electrons from the ligands. So the complex, that is the CuCl5 3-. We are having the first of all the 3d atomic orbital, then the 4s atomic orbital, 4p atomic orbital, and lastly the 4d atomic orbital. These are the electrons as it is, the 9 electrons in the 3d shell. Then this is the first electron from the first ligand, then the second pair of electron, third pair of electron, fourth pair of electron and the fifth pair of electrons. So these are the 5 electrons, or we can say that these are the electrons from the 5 Cl- ions. From this we can say that there is a single unpaired electron. This is the first unpaired electron which is in the 3d atomic orbital. From this, the 4 3d orbitals of the Cu2+ ions contains 4 pair of electrons and the fifth 3d orbital contains an unpaired electron. The empty 3p and 1d orbitals of the outermost shell, that is the fourth shell, undergoes hybridization and provide a space to accommodate the 5 pairs of electrons supplied by the 5 ligands, which are the 5 Cl- ions. Since there is one unpaired electron present in the complex, it is paramagnetic in nature. Then further we can say that the calculated magnetic moment of the ion is 1.73 bm. Why it is 1.73? Because it is having one unpaired electron. The central metal ion, that is the Cu2+, undergoes sp3d type of hybridization, which suggests the trigonal bipyramidal geometry. So this is the trigonal bipyramidal geometry for the CuCl5 3- ion. At the center we are having the metal and it is surrounded by the 5 ligands in a trigonal bipyramidal fashion. Then Other examples are, the first one is the MnCO4NO, second example is the NiCO5, third one is the NiCN5 3-. So these are the examples for the dsp3 type of hybridization or sp3d type of hybridization. Further, after this we are having the octahedral complexes. So these complexes, they are formed by the D2sp3 or sp3d2 type of hybridization of the metal atom or the ion, in which the d atomic orbitals, they are the dx square minus y square and the dz square atomic orbital. Now let's start with the first one, that is the D2sp3 type of hybridization. Now what is the D2sp3 type of hybridization? When two d orbital, that is the dx square minus y square and the dz square of n minus 1 shell, that means the last but 2, and one s orbital, that is the last shell, that is the nth shell, and the 3p orbital of the last shell, that is n shell, take part in the hybridization, then it is known as the D2sp3 type of hybridization. First example for this, it is CONH36 3+ ion. The electronic configuration for the cobalt atomic number 27 is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7, or argon core 4s2, 3d7. Then the oxidation number of the cobalt here is the +3. So the atomic number becomes 24. So we have to remove the 3 electrons. So the electronic configuration is the 1s2, 2s2, 2p6, 3s2, 3p6, 4s0, 3d6. We have removed 2 electrons from the 4s and 1 electron from the 3d. Or it is argon core 4s0, 3d6. So we have to put these electrons in the box diagram. So we are having the cobalt in the ground state, for which we are having the 3d atomic orbital, then 4s atomic orbital and 4p atomic orbital. So this is the first electron, second electron, third electron, fourth electron, fifth electron. All are unpaired. Then the sixth electron will be the paired. Then the excited electronic configuration of the cobalt. Again, for which we are having the 3d atomic orbital, 4s atomic orbital and the 4p atomic orbital, right? Now for this, we know that it is having the electronic configuration which is a D2sp3 type of hybridization. That means the 2 d orbitals and the 1s and the 3p atomic orbital, they should be vacant. Now here this 1s and the 3p, they are already vacant. Only we have to make these 2 3d atomic orbitals vacant. So in the excited state, these 2 electrons, they are paired up in the adjacent. So we are having pairing of this electron with the adjacent and pairing of these electrons with the its adjacent. So this is the first electron, second electron, third electron. Then fourth will be paired as it is, fifth will be paired and the sixth will be paired. So this is the electronic excited state electronic configuration in which the 2 3d atomic orbitals made vacant. So we are having the hybridization which is called as the D2sp3 type of hybridization. Then the complex ion, that is a CONH36 3+ complex ion. Again we are having the 3d atomic orbital, then 4s atomic orbital and the 4p atomic orbital. The first 3 pairs, they are as it is. This is the first one, second one, third one. Then the fourth one, fifth one, sixth one. These are the electrons from the metal ion. Then this is the first electron pair, second electron pair, third electron pair, fourth electron pair, fifth electron pair and the sixth electron pair. These are the 6 electrons pair. They are from the ligands, or we can say that these are the electrons from the 6 ammonia, right? Now from this we can say that there are no unpaired electrons, right? So further, the 4 unpaired electrons in the ground state of the cobalt 3+ ion pair up in the excited state. Thus 2 vacant d orbitals are created. Since all the electrons are paired, it is a diamagnetic in nature. Then the observed and the calculated magnetic moment of the complex ion is 0 because the number of unpaired electrons are 0. The pairing energy is supplied by the formation of the 6 strong bonds in the complex ion. Then the central metal ion undergoes D2sp3 type of hybridization which suggests the octahedral geometry. Now here we are using the inner d orbital. So the octahedral geometry for the CONH36 is like this, in which we are having the central metal which is surrounded by the 6 NH3 in an octahedral fashion. Then the second example is the FeCN6 3- ion. The electronic configuration for the Fe, that is atomic number 26, is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6, or it is having the argon core with the 4s2, 3d6. Now here the Fe is having the oxidation state +3, that means the atomic number is 23. So we have to remove the 3 electrons. The 2 electrons, they are eliminated from the 4s and 1 electron is eliminated from the 3d. So it becomes 1s2, 2s2, 2p6, 3s2, 3p6, 4s0, 3d5, or it is having the argon core 4s0, 3d5. So let's put these 5 electrons of the 3d in the box diagram. So we are having Fe in the ground state, which is having the 3d atomic orbital, then 4s atomic orbital and the 4p atomic orbital. So we are having the first electron, second electron, third electron, fourth electron and the fifth electron. So these are the 5 electrons of the Fe. Then this Fe3 plus in the excited state. What will be the excited state? We want the 2d atomic orbitals vacant, the 4s and the 4p, they are already vacant. So here again we are having the 3d atomic orbital, 4s atomic orbital and the 4p atomic orbital, right? Now first electron is shifted in the adjacent and second one is also shifted in the adjacent to make the 2 3d atomic orbitals vacant. So the unpaired electrons, they are paired up in the adjacent. So this is the first electron, second electron, third electron. They are unpaired. Fourth will be paired and the fifth will be paired, due to which we are having this D2sp3 type of hybridization. Then the complex, that is the FeCN6 3-. Again we are having the 3d atomic orbital, 4s atomic orbital and the 4p atomic orbital, in which the first 5 electrons, they are from the metal, 3 unpaired, then 2 paired. Then we are having the first electron pair, second electron pair, third electron pair, fourth electron pair, fifth electron pair and the sixth electron pair. So these are the 6 electron pairs from the 6 ligands, or we can say these are the electrons from the 6 cyanides. Now here instead of pair we are having the unpaired electron. Make this correction, okay? Here we are having an unpaired electrons. So this complex suggests one unpaired electron. So 5 unpaired electrons in a ground state of Fe3 plus ion pair up in the excited state. Thus 2 pairs are formed and 2 vacant d orbitals are created, as there is 1 electron unpaired. It is paramagnetic in nature and the calculated magnetic moment of the complex is 1.73 bm and the observed magnetic moment of the complex ion is 2.3 bm. This shows that some factors other than spin only movement contribute to the total magnetic moment of the complex. Here we can say that the observed and the calculated, these values, they are not nearby but they are varying. So we can say that some factors other than the spin only magnetic moment contribute to the total magnetic moment of the complex ion. The central metal ion undergoes a D2sp3 type of hybridization, which again suggests the octahedral geometry. So for this we are having the FeCN6 3-, which is having the Fe at the center and it is surrounded by the 6 cyanides octahedrali. Other examples are MnCN6 3-, CrNH36 3+, CrCN6 3-, COCN6 3- and CrCO6. Okay, so these are the examples for the D2sp3 type of hybridization. Now next type of hybridization for the octahedral geometry, which is sp3 D2 type of hybridization, in which we have to use the outer d orbital. So when one s atomic orbital 3p atomic orbital and the 2d atomic orbital, they are a dx square minus y square and a dz square of the same shell. That is the last shell, N shell. Take part in hybridization, then it is known as the sp3d2 type of hybridization. First example, Fe 3 minus. The electronic configurations for the Fe atomic number 26 is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Or we are having the argon core, then remaining as 4s2, 3d6. But here the Fe is having the atomic number 3 plus. So the atomic number becomes, Fe having the oxidation number plus 3, atomic number becomes 23. So we have to remove the 3 electrons. They are eliminated from the 4s and the 3d. So it becomes 4s2, 2s2, 2p6, 3s2, 3p6, then 4s0, 3d, 5. Or it is argon core 4s0, 3d, 5. So let's put these 5 electrons in the box diagram. So we are having the Fe3 plus, which is having the 3d atomic orbital, 4s atomic orbital, 4p atomic orbital, and we have to also consider the outer, that is the 3d. Instead of 3d, here it is 4d atomic orbital, not 3d. Okay, so this is the first electron, second electron, third electron, fourth electron and the fifth electron. So this 1s, 3p and the 2d, they are forming the sp3d2 type of hybridization. So the complex, that is the Fe 3 minus. We are having the again 3d atomic orbital, 4s atomic orbital, 4p atomic orbital and the 4d atomic orbital. The 3d, they are having the 5 unpaired electrons like this. Then the first electron pair, second electron pair, third electron pair, fourth electron pair, fifth one and the sixth one. These 6 electron pairs, they are from the 6 ligands, or we may say that these are the electrons from the 6 F minus ions. There are 5 unpaired electrons in the Fe3 plus ion. The complex ion is highly paramagnetic in nature. Then the central metal ion undergoes sp3d2 type of hybridization, which suggests the octahedral geometry. This is the octahedral geometry for the Fe 3 minus ion. At the center we are having the metal ion, that is Fe, which is surrounded by the 6 ligands octahedrali. Then the second example for this is the NiNH36 2 plus ion. Now the electronic configuration for the nickel with the atomic number 28 is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. Or it is having the argon core 4s2, 3d8. Then the oxidation number for the nickel over here is a 2 plus. So it is Ni2 plus, atomic number becomes 226. So we have to remove the 2 electrons, and these 2 electrons, they are eliminated from the 4s. So we are having the electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6 and then 4s0, 3d8. Or it is argon core 4s0, 3d8. So we have to put the 8 electrons in the 3d atomic orbital. So the box diagram for the Ni2 plus, it consists of 3d atomic orbital, then 4s atomic orbital, then 4p atomic orbital, then 4d atomic orbital, right? Instead of 3d again, over here it is the 4d atomic orbital. So we are having the first electron, second electron, third electron, fourth electron and the fifth electron. Then the sixth will be paired, seventh will be paired and the eighth will be paired. Now here it undergoes the sp3d2 type of hybridization. There is no need to go the excited state because the 1s, 3p and the 2d, they are already vacant. So it shows sp3d2 type of hybridization. So for the complex ion, which is NiNH36 2 plus, we are having the 3d atomic orbital, 4s atomic orbital, 4p and the 4d atomic orbital. Again the electrons, first of all from the metals, 5 are unpaired and the remaining 3 will be paired. Then the first electron pair, second electron pair, third electron pair, fourth one, fifth one and the sixth one. These are the electrons, they are from the ligand, that is the 6 ammonia ligands, or we can say these are the electrons from the 6 NH3. Further, we can say that there are 2 unpaired electrons in the Ni2 plus ion. The complex ion is paramagnetic in nature. The central metal ion undergoes sp3d2 type of hybridization, which suggests the octahedral geometry. So, the octahedral geometry for the NiNH36 means we are having the nickel at the center and which is surrounded by the 6 NH3 octahedrally. Other examples are, the first one is the COF6 3 minus, FeNH36 2 plus, CrH2O6 2 plus, and ZnNH36 2 plus. Okay, so these two videos shows the valence bond representation of the tetrahedral complexes, then square planar complexes. Third one is the trigonal bipyramidal complexes, and lastly we have studied the octahedral complexes. Thank you.